All right, welcome to our third session here and today we're going to be covering probabilistic models and evaluation of probabilities output from these models. So we're going to talk about the nature of probabilistic models, and we're going to use that to understand ROC curves, receiver operator curves. And then we're going to talk about precision recall curves, area under the curve, which is a way of a performance metric that you can use to evaluate your models. And then we're going to end with model calibration. How can you compare the distributions of your model's probabilities to the real world representation? And if they aren't matching up and aligning, how can you force your model probability distribution to be the same as your real world scenario? So we are now here in session 3, probabilistic model evaluation, and we have these sessions to go. I said I would eventually condense these and figure out what they would be. I finally have done that, so we will not have 9. As I said, we only have 8. So moving forward, it's regression metrics, advanced classification metrics, model selection and cross-fold validation, cross-validation, some advanced techniques. So I combined and simplified a few things under advanced techniques, and then finally completing with the ethical considerations because I do think that is important. Okay, so diving into session 3. Again, in here I have the learning objectives. So if you want to know what should I focus on learning from today, what are the things that I need to be aware of, it's really these ROC curves, the precision recall curve, the area under both of these curves is kind of the content I want you to take away from today. Model calibration, it's good for you to know, but you'll notice our breakout exercises and your homework assignment doesn't focus on it a ton. It's just a topic that fit well here. But as far as performance metrics, knowing these are more important foundationally. Okay, so I put model calibration as an extra exercise today. You can do that if you're interested, kind of look at that notebook, but we're going to focus on, like I said, AUC, PR. So let's dive in. All right. Oh, are there issues with StreamYard? Oh, Ted, there we are. Are you in now, Ted?
It's a bit choppy, so I'm not sure what my problem is here.
You're a little choppy to us as well. You're coming through just a bit choppy.
And everything is coming clear here.
Okay, we'll keep moving here. It's all set up. There we go. Sorry. Arrange this so I can look at the screen. Here we are. So we're again, this is our agenda for today. We're going to talk about prediction probabilities, thresholds, which we've all discussed before in the previous class. We're going to refresh on that, make sure that we understand that, because we're going to use that to build a foundation to really understand what a ROC curve is, what a PR curve is, what area under the curve represents, and then again, diving into model calibration at the end. Okay, probabilistic models and ROC curves. So probability is in the context of statistics and machine learning. Sorry, I'm going to adjust one more thing on my main screen here. Forgive me. There we are. Just so I can see the next slide. So probability in the context of statistics and machine learning, it represents the likelihood that an event will occur. So it's a numerical representation from 0 to 1 and indicates how likely it is that something will happen. Values closer to 0 are more improbable, and values closer to 1 are more certain. This is kind of like probability theory. This is the theory of probability. And it's the likelihood that an event will occur. So for example, you take a coin and you toss it. What's the probability that a coin lands heads up, or the probability of this outcome versus another outcome? Similar to that, in binary classification problems, the output of a model indicates the likelihood of a data point belonging to a certain class. What is the probability that this is a banana? What is the probability that this is an apple? Is it 0.8? Is it 0.7? So what's the likelihood that what you see, or what I'm predicting here, is of a certain class? So probability, by definition, it quantifies the uncertainty, and it represents the degree of belief or the degree of confidence that we have in an event occurring, in the event that that is true. What is the probability that this transaction is fraudulent? It represents the model's degree of belief, its confidence that that is a fraudulent transaction. It can have a high degree of confidence, 0.8, 0.9, or it can have a low degree of confidence, meaning it's less likely that it is a fraudulent event. So we usually, in predictions, we don't usually say we strongly predicted that this was or wasn't fraud. It's more of a soft gradient. It has a higher likelihood of being fraud, or these are the things with a lower likelihood of being fraud, because we know we all live in a probabilistic world. Not everything is black and white. Everything is represented by probabilities. And so in that probabilistic nature, some of your predictions will be right and some of yours will be wrong. So machine learning algorithms, that's kind of the theory of probability. Machine learning algorithms try to output probabilities through various mechanisms, basically through various algorithms. By the algorithms that they employ, everything we talked about in the last class, these methodologies attempt to output probabilities assigned with given classes, if we're talking about binary classification. So logistic regression, which we spent a lot of time on last class, it outputs a probability that something belongs to a given class using that logistic function, using that sigmoid function. Remember that S function that kind of mapped the probabilities to either 0 or 1 among an infinite range of input ranges. That's logistic regression. So that's the it outputs a probability between 0 and 1. It's the probability 0.2, is it 0.7? Decision trees can also output a probability. They have a different mechanism that they use to do that. The class can be inferred from the proportion of training samples in a leaf node. So if you have 10 leaf nodes and 1 training sample in each leaf node, maybe each of those represent a 0.1 probability. So this is just, in random forest, like we talked about being a bunch of decision trees, maybe each tree, maybe there are 100 trees, and each tree represents 1% of that probability vote. And so if 70 of the 100 trees vote 1 and 30 of the 100 trees vote 0, then maybe it's a 70% probability. There's a higher confidence, a higher certainty, a higher likelihood, because more trees are voting yes than the majority of trees are voting yes, because 0.7 are voting yes. So the output is a probability. Sorry, I just wanted to make sure we're in the right spot for the slides. We are. Okay, sorry, I was second guessing myself. So the output is a probability value between 0 and 1, representing the likelihood that an instance that an input belongs to the positive class, or an instance belongs to the positive class. Okay, this is just kind of refresher, reorienting on probabilities, because this is all we're going to talk about today, are the probabilities output by these models. So a threshold is, in the context of these machine learning and classification, specifically binary classification, if we want to really simplify it, A threshold is a value that separates the predicted probabilities into different classes. So we have all these thresholds. We have 0.1, 0.2, 0.3, 0.4, 0.5. We've got 0.55, 0.555. It's a continuous range. It's essentially an infinite range. Somewhere in there, we have to draw a line in the sand and say anything greater than this value is a 1 and everything less than this value is a 0. And that's what a threshold is. It's used to make decisions about which class a data point belongs to. And it's based on the probability output by the model. I might have just already said all this. So how it works is binary classification models output probabilities. Each element, each prediction has a probability associated with it for most machine learning algorithms. By the way, not all machine learning algorithms output probabilities. A lot of them, if not most of them, do. So we then apply this threshold to the probability output by the machine learning model. So we can decide, is it a 1 if it's above this threshold, or is it a 0, basically, if it's below this threshold? I should have put in here the default for most, if not all, machine learning algorithms. I don't want to say all because I could technically be missing something, but the output for most machine learning algorithms is 0.5. So anything above 0.5 is a 1, anything below 0.5 is a 0. There are reasons why you might want to change that, but that's the default setting. Okay, so here's an example. If we had a logistic regression model. This is our classic spam example. Spam is our positive class, not spam is our negative class. If the model outputs a probability of 0.7 for any given email, we don't know whether this email is spam or not. We're given an email and the model says, I'm 0.7. That's my probability that this is spam. If our threshold is set to 0.5, which it is by default, the email will be classified as spam because the probability exceeds that threshold. However, if the threshold is set to 0.8, the email is now not spam. We now classify it as not spam because the probability does not exceed that threshold. So that's how it works. It changes what you predict, whether it's spam or not, based on the probability. The probability didn't change in this example. It was always 0.7 for that email. Our threshold changed for what we classify as spam versus not spam. Is it over 0.5 as spam or is it over 0.8 as spam? Okay, so in summary, thresholds are an adjustable parameter that can be tuned to control your trade-off between precision and recall, or I should have maybe not said precision and recall because we're going to talk about something else first. It can be used to control your trade-off between some values that you're trying to assess. And by varying that threshold, we can prioritize certain types of errors over other types of errors, depending on the requirements for our application. We have quite a few breakouts today. So I have they're just two breakouts like normal, but each one has 2 parts. So we're gonna do 2-part breakouts. So if you download the thresholds and ROC, this is the one we're gonna start with today. So let's consider a scenario with actual data because it's a little easier to talk about thresholds if we actually have something to look at and compare against. So we're doing our spam example here, and we have a model that puts out probabilities for each email, whether or not they're spam. And what I want you guys to do here is to adjust the threshold to see how it affects the model's precision and recall. We're just gonna start by observing that. So here, we're gonna load in some data. So you're gonna run this function, and then we're gonna create some sample data. I'm gonna make some fake data here. Here's some true labels. This is what it really is. This is our ground truth. our ground truth says it actually isn't spam, or it actually was spam, or it wasn't spam, or it was spam. And then here's our predicted probabilities. So you can see for this example, we were really confident that it was spam, but it was in fact not spam. And this one, we were pretty confident it wasn't spam, but it in fact was spam, and you can kind of go down the line there. So our default threshold is 0.5. So now we're going to take our predicted probabilities here, and we're going to transform them into predictions, into discrete 1, 0 predictions. So we have our predicted labels default. It's where predicted probabilities is greater than equal to 0.5. And then we're just going to cast them to an int to be complete there. And then we're going to run precision score, which we're importing from sklearn up here. We're going to pass our true labels and our predicted labels that we created here. We created some predicted labels off of these probabilities. And then we're going to call recall score, which again, it's an sklearn metric, or you can implement these yourself if you're really feeling like doing that. But you can just call sklearn true labels and the predicted labels default, and then we're printing those out. So spend just a few minutes here, try adjusting the threshold to 0.3 and observe the difference. Here's the precision and recall with the threshold of 0.5. We'll give you guys just a few minutes, maybe spend 5 minutes on that, 6:27. All right, were you guys able to get this to run at a threshold of 0.3?
Yes.
Awesome. Anybody want to share their code or what they changed?
I just went where it said 0.5, I changed it to 0.3.
Perfect. Let's do that. And prints 0.3. Change the comment for completeness. Oh,
You didn't run.
I think I have to run my other cells. There we go. I just lost my my loaded values here, so here we are. So here's the difference. What are the big changes that you guys noticed between precision, between a threshold of 0.5 and a threshold of 0.3?
Well, if you round up, they're basically the same.
That is a good point. The precision is the same if you round up. So the precision didn't really change if we round up. What about the recall?
Less false positives.
Less false positives. Why is that?
Because only pulling out those values with the threshold of 0.3. I'm sorry, with a greater than or equal to 0.3, found more values that were positive.
That's exactly right. So if we decrease our threshold, we're predicting 1 for a larger amount of events. So we're going to have less false positives because less false negatives. Is that correct? False negatives? I think that's right.
Yeah.
Less false negatives because we're predicting 1 for more things. So we're instead of saying, if our data was well distributed and saying, instead of saying 50% of our data are ones, we're now saying 70% of our data is ones. We're predicting 1 for 70% of our data. So we're opening it up to a much larger proportion of our data set we're predicting as ones. So in theory, we should be capturing more of the ones. Less of the ones should be slipping through the cracks and missing our attention. So there should be less false negatives. Now we are going to see, yeah, go ahead.
I just played with that and just changed it to 0.1 instead of 3.
Good idea.
And now I'm seeing a threshold of 1 or a recall of 1. So it's showing no issues at all on recall now. So all we're doing is by lowering the threshold is including more of the positives that we got. In this scenario anyway, I'm not sure if that follows for all scenarios.
We are, say your last sentence one more time.
So
I'm going to turn, 1 second. Hold on, not quite yet. I'm going to turn up my volume a little more. Okay, now say it again.
So, okay, my question, I guess, is all we're doing by lowering our threshold is including more of the data set so that it ends up being, will that always be the case? Will recall goes to 1 to lower the threshold?
If we lower the threshold all the way to 0.1 or 0.00001, we get really, really small, we approach 0, our recall will always go to 1 because we are now predicting 1 for almost everything. So we are recalling everything we possibly can, unless we really for sure thought that it wasn't a 1 and we had our probability was 0.000000001. So yes, our threshold, as our probability threshold approaches 0, our recall approaches 1. On the flip side, such a great insight. Let's try it the other way. Let's crank this puppy up to 9. Ignore what this says down here about 0.3, by the way, because I'm not changing the text every time. So just pay attention to what I have up here and not there you are. So pay attention to what's up here. Let me make it a little lower. There we go. 0.8, so that's interesting. So our precision at 0.8 is 0.5, and then our precision, and then we change it to 0.9, and suddenly it's 0. Remember, our data set is up here. Why is it 0 at 0.9?
Is that because we only had 1.9 in our predicted probabilities and that ended up being a 0?
That's correct. So we only have 1.9. So threshold is based on the probabilities output by the model. And this model, along with many other models that you will use, very rarely will you actually see it have a very highly confident score, meaning 0.99. Most of the time, you're going to see very conservative ranges like this, 0.2, 0.3 to 0.9. That's pretty standard. And so actually, we only really have one probability that is 0.9. And as I believe that was John that said that, right? John? Is that who? I want to make sure I'm giving the right person credit. Correct me if I'm wrong. As John said, if we map this back to the actual true labels, 1, 2, 3, 4 in. So 1, 2, 3, 4. That was actually a 0. So that was not a correct probability prediction. It was highly confident and it was wrong. So because of that, we have a precision of 0. We had one example where we predicted it. The prediction was 9, so we said it was a 1, but it was in fact a 0, so we were incorrect. Now, just for some, just to communicate a point, I'm going to change that 0 to a 1. So it was 0 here. I just changed it to a 1. I'm going to rerun this just to show something. So now that it's above 0.9, the precision is now 1 because we only had, so our precision is perfect. And I put that there because this is what you will tend to see, though it's not as concrete as recall, because like you said, there will be examples, like this just showed, there can be examples where you're highly confident and wrong. But generally, as you increase your probability threshold, usually you increase your precision. If you're not increasing your precision, you have a model that's doing something really weird, and you should probably go look at that. But typically, as you increase your threshold, so as you get close higher and higher, you're predicting a smaller and smaller amount of those to be a 1. You're saying only probabilities above 0.9, only probabilities above 0.8. So you're saying only situations where the model is highly confident do I actually want to predict a 1, where the model is really certain. And by doing that, you usually increase your precision and decrease your recall. Usually. This was an example where that was, I'm going to leave that there because that was the whole point of that. Okay. Any questions or comments over thresholds? Are you feeling comfortable with thresholds? How they work?
I think I get the concept.
Okay, good. Because we're going to apply them now.
Okay. I guess we'll test it out.
We're gonna test that out. So this class is about metrics. So we're gonna dive into a metric that is, sorry, switching my screens around. That is something called threshold agnostic. I did so good at that, and then I messed it up at the last minute. There we go. That is something called threshold agnostic. So most metrics that we've looked at before, I should have put a precursor slide in here, I'm realizing now. Most metrics we've looked at before, accuracy, precision, recall, just like in the exercise we just did, precision is dependent on a threshold. Recall is dependent on a threshold. You can only calculate the accuracy of your model if you've defined a threshold that says any probability above this is 1, any probability below this is not 1. This new metric that we're going to talk about, called the receiver operator curve, or more commonly in the field called the ROC curve, is threshold agnostic. It means it doesn't matter what the threshold is for your model. It calculates a performance metric for your model without defining a specific threshold. And so again, this is called the ROC curve, which I realize is saying the word curve twice, but that is how it's used, because ROC stands for receiver operator curve. So I do realize when you say ROC curve, you're saying receiver operator curve, but that is how it's used in the field and the industry, which I think is odd. But it's a graphical representation of the performance of our binary classification model across all thresholds. Okay, so every single threshold. So we just looked at 2 in our example. We looked at I have to remember now, 0.5, and we looked at 0.3. This does it across all of them. So starting at 0.1, 0.2, 0.3, 0.5, all the way up to 1. On the x-axis here is something called the specificity or the false positive rate. And on the y-axis here is something called the sensitivity or the true positive rate, which is something that you already know as recall. And I think I put that on another slide because it's kind of confusing. There are so many words that mean the same thing in here. But basically, at every point along here on the blue line here, this is our model. And it says when the threshold is 0, what is the sensitivity versus the specificity? You know, this is an XY plane. So what is the specificity value? What's the sensitivity value? And look up where those meet. So here it is when they're 0, and here it is when the threshold is 1. And then as we increase the threshold, so when the threshold is, say, 0.2, we can come up here and we can see this is the sensitivity versus the specificity. When it's 0.5, that's somewhere in the middle here, this is the sensitivity versus the specificity. When it's 0.8, here's the sensitivity versus the specificity. So this is the performance of the model at every single threshold value. Okay, we're going to talk about this more. So here are the actual definitions here. Here are the components that make up this ROC curve. Here's how you would read it. Along the, I want to make sure I say the x-axis correctly, the y-axis is the true positive rate, TPR, sometimes it is abbreviated. This is also sometimes called sensitivity. It is also recall. They're all the same thing. So I apologize for the many varying terms for the same thing. Unfortunately, that is there, but it is the same true positives over true positives plus false negatives, the same recall that you know and love. And then we have the false positive rate, which it measures the proportion of false positive predictions among all negative predictions. So we've talked about this before, but it wasn't one of the main ones that we learned kind of in that first session of the class. So we've talked about this in the context of the confusion matrix. It was that sort of extra box at the end that we sort of pointed to, and we said sometimes it's useful. That is this one. So this is the false positive over the false positives plus the true negatives. And then we have the threshold. The threshold is the value that separates the predicted probabilities into different classes, into 1 and 0. So at point 2, how many classes were 1, how many predictions were 0, how many predictions were 1. At point 3, how many predictions were 0, how many predictions were 1. And by adjusting this threshold, we can control the trade-off between the true positive rate and the false positive rate. Because as you see, the false positive rate and the true positive rate change as we adjust this threshold. Just like we were playing with in our example, at some point it tips and it becomes higher for one, and at another point it tips and it becomes higher for the other one. Okay, so when you're reading these ROC curves, you may have noticed there's this orange dotted line down the center. So basically, jumping ahead of myself a little bit, but what I'm saying is this third bullet point here, I'll jump back to these other two. The curve that follows the diagonal line here in the middle, this represents random. If you have a model that's below that line, you did something really weird with your model that's I've never seen before, so go back and look at it. But you can basically tell that this orange line, you could say, well, that's really not a very good model. It's just barely better than me random guessing. If you handed these examples to me and I literally clicked random, like pressed a random button generator and just gave you a random result, your model is barely doing better than that across all those thresholds. So regardless of sort of what threshold we determine on average across all these probabilities, really not doing very well. This is like a normal, this is like better. This is like, okay, you can at least say that your model is better than a coin toss, better than random. You can look at this and you're like, here's the dotted line and here's my model. I'm not terrible. If your line looks like this blue one, go buy a lottery ticket because you just made a really good model and you're gonna change the world. I never see any of them this good. Usually we're somewhere in between that green line and that blue line, but this blue line's really good. A perfect classifier, which you should be very suspicious if you make one that actually is a perfect classifier, but if you happen to do that, it would be coming all the way up, straight up this line here, and then straight across here. So this helps us visualize the model's performance as the threshold changes. And these are really typical kind of trade-offs. These are normal curves. If you're seeing like very varying differences in here, that means that there's probably something weird going on in your data, like class imbalance or something. So they can be very insightful. Okay, I think that's good for this one. So in summary, the ROC curve, it's a very useful tool for evaluating and comparing the performance of these binary classification models. And it provides insight into their ability to discriminate between 1 and 0 predictions, between positive and negative predictions or instances across various threshold settings, not a specific threshold setting. Okay, so let's try it out. Let's pop back into that same notebook. And we're going to do part 2. I have to remember what I'm asking you to do here. Oh, yeah. So here, so we had our example above. We had our, oh, no, that's later. Is that this one? Oh, yes. Okay, sorry. We're going to use this same example a couple times today. So here, we're going to make a classification model. We're going to make some classification data here. So this is just a sklearn function that you can use that makes fake data. So we're going to make some fake data here. We're going to split it into train, test, split, so we can evaluate it. And we're going to train a logistic regression. So we're just going to model equals logistic regression, that model from sklearn. And we're going to do our model.fit, and we're going to pass our x train, y train. Great. We got our logistic regression model. Okay, so now we're gonna get these probabilities out of a logistic regression. We picked a logistic regression because we can pull probabilities out of that. So instead of calling model.predict and passing our x test, we're gonna call model.predict_proba. That's gonna return our probabilities instead of the 1, 0. We're actually gonna get the real 0.1, 0.7, 0.8. We're going to get the actual probabilities out of the model. And we're going to slice it so we just get one set of probabilities. When you call predict.proba, it gives you both probabilities. It gives you the probability of predicting 0 and the probability of predicting 1. They will always sum to 1. The probability of predicting 0 is always 1 minus the probability of predicting 1. So I can even show you that if you're curious. So if we just look at this. Oh, sorry. You will always have two probabilities. Adding them together, this has negative e on it. Sorry, I should convert that to a more friendly format. But adding them together will always combine to be 1. I'm realizing it's not obvious by me printing this out because of the e to the -1, you'd have to move the decimal point over. But basically this is 0.6 and this is 0.4. This is 0.8 and this is 0.9 if we round up with the 6, and this is 0.1. This is 0.5 if we round up with the 7, and this is 0.5. If you don't know e to the -1, it's scientific notation. It means you move the decimal point over 1. It's annoying. Sometimes it puts it in that format when decimal points are really small. These aren't that small, but like this one's e to the -2, so you would move it over 2 places. So this is like 0.05, and this is like 0.95 for this probability prediction. Sorry, it doesn't look very good. It's kind of annoying. But the whole point is they will always sum to 1, so you do not need both. There's never a situation where you need both. You can always infer what the other one is by the one that you have. So if you have the predicted probability for 0.1, the predicted probability of the positive class, which is what most people grab. So we're slicing this. We're saying, give me all columns, or I'm sorry, I said that backwards. Give me all rows and just the second column. Remember, Python is a 0-based index. So putting a 1 here, you could either put 0 here or you could put 1 here because we have 2 columns. We have the 0th column and we have the first column. First meaning actually the second index. So so we're saying, give me all the rows. That's what this semicolon does. We're saying, give me everything, but give me the second column, which is the prediction for the probability of the positive class. So all these are the predicted probability of the positive class. So if I say the predicted probability for a positive class was 0.7, what is the predicted probability for a negative class? You should be able to say it's 0.3 because it always sums to 1. All right, so this calculates your precision recall curve. And so we're calling this a ROC curve, which is a sklearn class. I just imported it. And we're passing our y test and our probs, our probabilities. And then out of that, we're going to get our thresholds, false positive rate, true positive rate. And then we're calling ROC AUC. And basically we create this receiver operator curve, this ROC curve. So here's the ROC curve. We just made some fake data and we trained a logistic regression and we built this ROC curve. This is random guessing. And here's our model. Your task is I set up some more data here. I generated some random probabilities for a positive class. So what we're going to do is, this is a trained model. We're going to look at the difference between a trained model and a random model. So I made some probabilities that were just random probabilities, and then I made some random true labels. So this is representing, what if you had some labels and I just picked a number out of a hat and handed it to you? Just so we can see, I know I told you it was this dotted line, but we're going to visualize what this looks like by actually running an exercise. So compute the rock curve and the area for the positive class and plot the curve in the same way that we did here. We computed the rock curve and then we plotted the curve. Do the same thing, but use the probs and true labels instead. Let's spend a little bit on this. Let's spend 10 minutes on this. 7:02. Let's come back at 7:02. All right, we're back. Is anybody able to compute the ROC curve here? Is anybody able to compute this?
All right, I'll throw mine up.
All right, awesome. Thank you. And let me stop the ticker thing here.
So I'll put it in the chat.
Excellent. Beautiful. I'm going to put this up here. All right, we have our false positive rate, and we're renaming these just not to have them confused with the one from above. We are calling the rock curve and passing the true labels that we created here and the probs we created here. And to rock AUC2, which we're going to rename with a 2 at the end, just not to confuse it from the one up above. We're going to calculate AUC, area under the curve, which we will talk about in a minute. So I realize we're jumping ahead of ourselves a little bit there. Using our false positive rate 2 and our true positive rate 2. Excellent. Is anybody able to plot the curve here using the values generated here? Excellent. Let's put this in here. Thanks, John. Have to we'll break this out as we go here. So we have plot the rock curve. So we're going to create our figure. We are hold on. I'm going to get these all on separate lines for a second.
Sorry.
No, you're fine. That's not you. That's the nature of the technology. Here we are. Oops. All right, and then plot.show. Oh, I forgot one. Is it? Here it is. There we are. All right. So this is total randomness. We just completely pulled numbers out of a hat and tried to calculate the ROC based off of a model that was predicting complete randomness, not at all similar or not at all using the data to make informed predictions. So what do you guys think about the difference between this blue line that we see here and the blue line we see up here? This one's much worse. So we can see that this red dotted line, which we had said was random guessing, is actually fairly representative of what random guessing would look like. Obviously, if we had more predictions, larger data set, it would get closer and closer to this red line. We have a fairly small data set here with just 100 samples, so it's not very large. There's not going to be a lot of points here. But this shows that that is random. That's about as bad as our model can get here. So anything that approaches this red line here is going to be a bad prediction. Okay, let's jump back. And let's talk about the area under the curve, AUC. Arrange my screen here. So the area under the curve, and we're going to talk about the ROC curve. And in context of that curve that we just discussed and you just plotted, the area under the ROC curve represents the overall performance of the classification model across all possible thresholds. So this is how you get one discrete value out of your ROC curve. If you want to say, what was the AUC of the ROC, of your ROC curve? This is that discrete value. It's a one-time value. While the ROC curve is measuring the probabilities, is measuring the performance across all of the thresholds, all the probability thresholds, the AUC is in fact taking the area underneath of that curve and calculating what is the area under this, and that is the score that we're going to get out of this. So if we look at this one, for example, this blue line here, it would be all of the area underneath this blue line. So everything under here, everything under here, everything under here, all of this would be colored another color. So in this oversimplified example here, we have a line that represents random, an AUC of 0.5, an area under the curve of 0.5 is completely random. That is that is us just taking a coin and tossing it. So if you train a model and your AUC is 0.51, that may be good in some types of performance metrics, but in terms of AUC, that is not a very strong performance metric. That's barely better than random. You're essentially random at that point. A perfect AUC, in theory, which never truly happens in practicality, but would be 1, where our true positive rate would just go straight up to here, and then our false positive rate would go straight over to here. So an AUC of 1, because the area under this curve, the area under this line is equal to 1. So AUC values, they range from 0 to 1. In all practicality, you will only see performance values around the range of 0.5 to 1, and closer to 1 is a better performance metric. So the point of an AUC is it is a single metric that quantifies the overall performance of binary classification models over all possible thresholds, all possible probability thresholds. So, and it measures the area that is underneath that ROC curve. We just talked about this. I don't know if I need to re-say this, but the way that you would interpret the AUC is a AUC of 1 suggests perfect classification performance, meaning that it achieves a true positive rate of 1 and a false positive rate of 0 across all threshold settings. And an AUC is of 5.5 is no better than random guessing. So the advantage of area under the curve is it is a threshold independent metric. So it evaluates the model's performance with no need of choosing a specific threshold. So when you calculate the precision of something, I should be able to tell you, hey, can you calculate the precision given this threshold? You should always know that precision, accuracy, recall, those things require a threshold to be calculated. The AUC is threshold independent. It's an average across all of those thresholds. The limitation is kind of the other side of that advantage. which it doesn't really provide insight into the model's performance from an operational standpoint. Because when you actually implement the model, you do have to choose a threshold. At some point, you have to say you are predicting 1, and you have to say you are predicting 0, and you have to be consistent about that. So from an operational standpoint, it doesn't necessarily represent how the model will perform in the real world, per se. It's more of an understanding of how the model is making the decision across those various thresholds. And the ROC curve may not be suitable in certain situations. So when we're looking at the cost of false positives and false negatives, and they are very different, and there's very different penalties for a false positive versus a false negative, AUC may not really be an appropriate metric for that. All right, so area under the curve. AUC is typically referred to as area under our ROC curve, though we're also going to talk about the precision recall curve and something that's usually referred to as the PR-AUC. So just know when somebody say AUC, area under the curve, just know to ask whether it is the ROC curve or the precision recall curve. I don't think we did our breakout yet for this one. Okay. Let's jump into our next breakout. So open the second notebook here. Oh, let's take a break. Sorry. I forgot to put breaks in my slides. Let's take a 10-minute break here. Come back at 7:25.
worry, it's going to be like 5 hours to figure it out.
We are back. Okay. And we're going to jump right into our breakout. So if you guys could, sorry if it's noisy, there's a vacuum. I apologize for those online. If you could jump into this breakout AUC and PR curve, we're going to talk about AUC in context of the ROC curve first, to our receiver operator curve. So your task here will be to calculate the AUC for each model and compare them. So I have this code that we just did before. This is the same code. We have our curve here, our ROC curve from our first model. And we have our ROC curve here for our random model. So we've got our logistic regression and our random model. What I want you to do under each of these ROC curves, can you calculate the AUC? So for this first one, you can just use the sklearn metrics AUC curve. You can just go look up sklearn metrics AUC. There we go. So you're just going to use this this function here, which they have many examples. We're just going to do the binary case, so ignore multi-class and multi-label at the moment. We're just going to use binary. So calculate the AUC here. You know what? We might have even already done this above. I think we did, so it should be easy. And then calculate the AUC for this one as well using sklearn AUC. So sklearn metrics AUC using this one. And there is an example right here. And I think we actually did this earlier in the code. I'm now realizing I'm a little ahead of myself here. So you can just probably look at that and figure it out. Let's just do 5 minutes on this. And let's jump back and talk about precision recall curves at 7:33. A quick one here. All right, coming back here. Is anybody able to calculate, let's start with the first one, the AUC, and I realize it does say it on here, but calculate the AUC for this here. Anybody have code they would be willing to share in the chat?
I literally just stole yours already there. So
Perfect, let's do that. So I actually think I have this one. Okay, grab that. Here we are. I'm gonna calculate the AUC for our logistic regression model. So here we're gonna use the ROC AUC score. We're gonna pass Y test and then the probabilities. Order here is important. It matters which one you pass first. And then we're gonna calculate our AUC for logistic regression. I have to read that next, I apologize. Here we are. So 0.9216, etc. And you see that we can actually have that plotted on our graph up here. Okay. What about this one? I'll just drop this answer in as well because it was the same as was in the code up above. So we're just going to calculate AUC, passing the false positive rate and our true positive rate to the AUC function and calculating the AUC. Oh, I have to rerun this. I apologize. It's not the proper AUC. I didn't rename my variables as John did, so that's why it overwrote when I reran that. So rerunning that cell to overwrite my false positive rate and true positive rate again, we now get that AUC of 0.48. If you guys want, I will give you 5 points of extra credit if you color in the area under the curve. So if you make a graph that visualizes the area under the curve as the shaded region with both graphs. Okay, let's jump back into precision recall curve. Totally optional, 5 points, not required at all, bonus points. Okay, precision recall curve. The precision recall curve, it's a graphical representation of the trade-off between precision and recall for binary classification problems. That's the domain we're going to talk about it here. For various threshold settings. So again, this is another metric that is agnostic of the threshold that you set. It looks across all of the thresholds, but instead of evaluating sensitivity versus specificity, instead of evaluating the true positive rate plus false positive rate, we're evaluating the precision versus the recall. Okay. So it's when we look at the area under the curve for this one, again, we can do the same thing, look at the AUC, the area under the curve, to get one representative value of how that model performs across all the various thresholds to quantify that overall performance across threshold settings. And it's usually called the AUC-PR, so area under the curve for the precision recall curve. And just the same as the other AUC, a higher value indicates better model performance and indicates higher precision and recall across all those threshold settings, all the threshold settings. We are trying to maximize this metric. Again, I'm really sorry for the vacuum. So TPR, the true positive rate and recall. Is the true positive rate the same thing as recall? Yes, the true positive rate and recall are the same thing. I just don't want any confusion here. So if we look at this graph and we have recall and we have the true positive rate, notice they're on different axes. On this one, the true positive rate is on the y-axis. On this one, the true positive rate is on the x-axis. So they're in different locations, but they are a measurement of the same thing. It is the exact same thing. Both terms refer to the proportion of true positives over true positives plus false negatives. So it's the proportion of true positives among all actual positive predictions. So they both carry the same formula. It's TP over TP plus FN. They're commonly used interchangeably in problems, and just note that it's also sometimes referred to as sensitivity. So true positive rate, recall sensitivity. All right, false positive rate, the other dimension that we use on this ROC curve. Is the false positive rate the same thing as precision? Are these the same thing? Are these the same graphs? No. The false positive rate and precision are not the same thing. The false positive rate here measures the proportion of false positive predictions among all negative instances. So it's FP over FP plus TN. Remember, we talked about this in session 1, false positive, we didn't talk about false positive rate. That's false positive rate. The precision measures the proportion of positive predictions among all predictions made by the model. So of the predictions that we make correct, of the predictions that we make as positive predictions, how often are we correct? It's the true positive over the true positive plus the false positive. That's precision. Whenever we say we're certain that this is a prediction, that this is the right prediction, of all the times we say that, how often is it actually the right prediction? How many times are we falsely positive? The false positive rate is a proportion of false positives among all actual negative instances. Okay. So they're different things. So they measure different things, and there are scenarios in which you might want to use one versus the other. So they both give an understanding of model fit, how good of a fit is your model. And they both they can help you kind of choose a threshold for model performance. You can say, hey, I have the right balance of precision and recall when I choose this threshold here. Or I have the right balance of my true positive rate and my false positive rate when I choose this threshold here. When you might want to use a precision recall curve over a ROC curve is when you have class imbalance. So if you have class imbalance, the precision recall curve is going to represent that just a little better. And the ROC AUC is better when there's balanced class distribution of the data. So it really just comes down to class imbalance. Precision recall curve, if you're dealing with fraud, or if you're dealing maybe with medical diagnoses, it's going to be a better situation to use the precision recall curve because it'll really give you that trade-off. Okay. Like we have one final breakout, and then we're going to take it home with model calibration. So last breakout, precision recall curve here. I would like you to, of the two examples that we just talked about, so the same data, I would just copy paste or whatever you want to do here to make these the same examples. instead of plotting the true positive rate and the false positive rate, I'd like you to try to plot the precision versus the recall. So try to do that for our logistic regression example and our random model example. So we had a logistic regression was this first block here. So try to do it for this, these model probabilities, and then try to do it for the random model probabilities as well. Let's spend a good amount of time on this. Let's spend 20 minutes on that. We'll combine it with the break. Then we'll go through model calibration and we should be good for today. So let's do, what would that be? 04? 804? Is that right? Okay, I'm coming back just a little early. Logistic regression model example code here. Anybody were you guys able to make a precision recall curve for the logistic regression model? Anybody want to share their code?
I got one, but I was working on the awk PR, and I never got that done.
Excellent. The op PR. This one, the random model?
No, down there in the bottom of your screen, under diagram, you have awk-PR equals 0.049, or
Oh, yes. This
I didn't
one.
know how to calculate that. I was messing around with sklearn to figure that out, but I didn't get that figured out.
That is a good point. Do you want to share your code that you wrote for this, and then I'll share mine, and then I'll call on Anna, and she'll share a neat little function that she found as well.
All right. Do you want me to put it, which comments? Because this is going to be a lot of entering stuff.
Let's see. Can you put it in the Slack channel, and then on your keyboard there is a little thing called a tick symbol, and it looks like, I'll put it what it looks like in the chat. It looks like that. If you hit that 3 times, tick, 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 and then it should just pop up like a box inside of your chat window. Paste it into that, and it will convert your code. It'll keep the integrity of your code as code. Try, instead of the quotes, try the tick function. Like it should be right above your tab button on your keyboard, right where the tilde. Yeah, beautiful. There. Now it looks like code. So then when I paste it in, I won't get any weird things here. Awesome. Excellent. So we're going to run this. You know what? There are going to be things that are renamed, would be my guess. So let's see. Yeah, so we have precision recall 1 right now. It's
Oh, you're getting the error because of this. Okay, go up. I have one line of code you need to comment out for now. Comment out the Prex score 1 line.
Oh, you got it.
Not that, the next one down.
Oh, next one down. Oh, correct, score
That
1.
line.
Here we are. Run that. Let's see. This is, what about that? This is saying, oh, because it's using, correct score 1 is not defined. So it's trying to use.
Okay, just get rid of
Oh, here.
the end of that. Yeah, just put a quotes in there or something. There.
I don't understand.
Oh,
We are
sorry.
just gonna.
I just turned on my Siri on accident. It scared me. I don't know if you guys heard that on the thing, but I heard that. You know what? Anna and I are having the same issue with her curve. Getting it, it was plotting in the, hey, you got the coloring, the shading under the curve here. Nice. That looks really good. Anna, do you want to share your code that you wrote that uses a different function than what we had discussed here? So Anna found a sklearn function that she's going to share. That is a lot simpler. So if you guys want to plot this in the future and you don't want to go through all the matplotlib things, their sklearn.metrics has a precision recall display function. And to this display function, you can call from estimator, and you can actually pass your model. So you don't have to calculate the probabilities and then pass the probabilities. You actually pass your whole model object, and then you pass X test and your X features, and then you pass your true labels. And under the hood, it will run the probabilities for you and calculate the precision and the recall for you. And then it'll display this, and then you can just change the name of your title graph to whatever you want here. But if you're looking for a very easy way to get a precision recall curve that also gives you your area under the curve score here as well, you can use this function. It's quite literally 2 lines of code here. This just looks like 3. There we go. So good find there, Anna. I will share the code that I have as well. I just have to find it here. This is what I have. Okay, so this is the code that I have that produced that graph as we saw it above. So the AUPR that you were asking about, John, that is from right here, calculating the AUC, passing, recall, and
Ooh. So you're still using the AUC function for that. Okay.
using the AUC function for that. I'm hesitating if that's correct now that I look at it. So let me think about that for a minute. I may ping in the Slack channel that I was technically wrong there. So, but that's what I did for that. And then passing recall and precision, and then labeling recall and precision. The rest is just labeling stuff. So similar graph function to what we had before. You can do the same thing for the random graph. I did something goofy here. Oh, I have to go. I didn't rename things, so I have to rerun my random data here. Here's the random data. So there we are. I had to rerun that real quick. There we are. So here is the precision recall graph for the random samples. So I just want to note that random for a PR curve looks very different from this visual than random from the AUC graph that we saw. You can see it's pretty much a line, it looks like, at least going across here. But whereas the AUC rock curve that we saw was a diagonal line going this way. So they look very different. All right.
The top code is that one here. Okay.
Yeah, this was the one for the logistic regression, the actual model that makes somewhat informed decisions. All right, I think we're gonna close out the evening here with model calibration. So we've sort of been building to this topic. We've been talking about model probabilities, and we've been talking about thresholds and all these different things. Taking one step back here before we dive into model calibration, just to understand what is a probability. We touched on this at the beginning, so I'm coming full circle here now. Many machine learning models predict probabilities. Many machine learning models like logistic regression, support vector machines, SVMs, output probabilities rather than discrete prediction. So they'll put, instead of saying 1 or 0, under the hood that's a probability of 0.8 or 0.2. And these probabilities represent the model's confidence in its prediction. How sure is the model that it is a prediction of 1 or a prediction of 0? What's the level of confidence? When we think about events in the world, in probability theory, there are a lot of distributions that represent events occurring in the world. So we're not going to dive into this, but I just want you to be aware that there are a lot of different ways we can represent distributions of probabilities. We're going to touch on two that you are probably familiar with. One is the uniform probability. So let's think about rolling a dice. You've got a 6-sided die. The probability of getting a 1 is equal to the probability of getting a 2, which is equal to the probability of getting a 3, which is equal to the probability of getting a 4, equal to the probability of getting a 5, equal to the probability of getting a 6. There is a 1/6 probability for each of those events occurring. The likelihood that that event occurs is uniform, meaning it is the same for every event. So this is a uniform probability distribution. They have equal likelihoods of the event occurring. So I just want to describe to you that this is the shape of a uniform probability distribution. The other probability distribution that you've probably heard of is the normal distribution. It's sometimes called the bell curve distribution. This is if you took everybody and you lined them up and you measured their heights, eventually it would become a normal distribution. Some people would be really short and some people would be really tall. And there would be kind of a peak here in the middle where most people are kind of like around this middle average height that's the same. You can also do that with grades. That's the example I have here, is you can get a normal distribution, a bell curve for grades. Some people are going to have lower grades. Some people are going to have higher grades. But in general, there will be a distribution where most of the grades kind of fall in this middle section here. So this is a normal distribution. And the reason I bring these up is because sometimes your data in the real world, you want to make sure that your predictions are fitting the distribution that you might expect out of your data. So when our model makes predictions, there are situations where what we are predicting doesn't always represent the real world distribution underneath the hood. So machine learning models obviously strive to approximate these real world probabilities, but there's a lot of complex situations which can lead to the predicted probability distributions not really reflecting the underlying real world probabilities. So if there are assumptions within your model, we talked about linear regression. There's assumptions within linear regression, especially when we're not relying on the law of large numbers and we're using smaller sample sets. And if those assumptions are violated, then there are situations where your probability distribution probably won't match reality. Feature representation, I won't go through all these, training data quality, the complexity of your model, class imbalance can make it really hard to have probability distributions that represent reality. And misinterpretation of the outputs, limited data if we have really small sample size. There's a lot of situations that can cause that. So to the rescue, here we have something called model calibration. And that's the process of adjusting your predicted output, your predicted probabilities of your machine learning model so they better represent the true probabilities or the outcomes of the events that you're trying to predict. So we want our probabilities to reflect the actual likelihood of predicted outcomes. Okay, pause here because I just threw it a lot at you, and I'll give you some examples. Let's take a really simple example first. I have two actual real-world calibrated models that I built for work. So the first one is fraud. When we predict fraud, it's a simple model, binary classification. It either is fraud or it's not fraud. When we predict fraud, sometimes the probability that our model predicts is so small that we never actually get any representation of our data set from our model. So we have to do two things. One is threshold adjustment, and the second is probability calibration. So let's think about fraud. Fraud, let's make up an example where fraud represents 2% of our entire data. If we look at the real world, that's our real world distribution. Our real world distribution is when we look at historical events where we have been able to identify fraud, we have seen it 2% of the time out of our entire data set. So ideally, our model should, for every 100 customers, it should predict 2 of those people as fraud. So if our model is well calibrated, out of every 1,000 predictions, it would predict 20 of those people as fraud. Do you see how the probability, the distribution, the representation of fraud predictions represents the proportion of fraud that we saw in our training data set? If our model predicted, say, 1% or say 0.5% of people having fraud, we would say our model is not well calibrated because it's not predicting the same proportion of individuals in its predictions as what we see in the training set.
I have a question.
Yeah.
So if you're saying we already have data stating the 2% is the average that you see throughout, all the other data that you have on that, you have to know that information in order to then know that the model calibration is not accurate, valid, whatever you call it.
That's such a great question. You do. And you're actually pointing out something I didn't put on the slides. That's a slightly more complicated topic, but which is that you do not calibrate your model on the same data that you trained it on. So yes, you would set aside some hidden data, kind of think of it like our test data, but it's a calibration set just for calibrating the model. And that's all you use it for, is to calibrate your model probabilities. So to your point, yes, you have to have tracked that historical data, and then you have to kind of set it away, lock and key, to make sure that you're not biasing your decisions.
Okay.
Yeah,
And is
excellent
that
question.
something you figure out like yourself, or is like your team come up with it, or like does like your stakeholders be like, hey, we don't keep an eye on this, or like?
This would be something that you would suggest as the data scientist.
Okay, so
You would
guys
say,
would be the one who suggests it, okay.
you would say, hey, during my model process, I made a really good model, but I also needed to calibrate it. I needed to calibrate it to the probabilities that we see in the data.
Okay.
So there are, like I said, in the fraud problem, there's 2 adjustments to make. So the first, let's talk about is a threshold. When your model predicts this person is fraud or this person is not fraud, I'm just telling you from experience, it's very likely that you will never have a probability prediction above 0.5. I never had a model confidently say with 0.9 probability that this is fraud. So you need to adjust your threshold so that you have that representation. So basically what you're doing is all of your probabilities are on this line from 0 to 1, but they're all squished down here. So you're not actually changing the way that your model makes the decision. You're just changing the order of the prediction probabilities. You're not changing the order of the probabilities. So you're not swapping them. You're not putting one prediction ahead of the other. You're just spreading them out on that graph. So we're just squeezing them out a little further so that we have some probabilities that actually are represented at that higher end. So maybe your probability only ever went up to 0.5. You're just going to stretch those out. You're just going to apply a transformation to them so that some of those probabilities, now the ones that were 0.5, the only 3 predictions you had at 0.5, those are essentially now 0.9s. Since your model never predicted anything as 0.9 anyways, you're going to stretch those out. You could either do it that way, or, so that's model calibration. You could either calibrate the probabilities, or you could do it the other way, which is address the threshold. So you could leave everything at 0.5. You say, yep, everything only ranges from 0.1 to 0.5, but instead I'm going to set the threshold at 0.4. So it's just a different way of doing it. So you could say anything above 0.4 is now fraud. So now you adjust the threshold to a point where you get that percentage representation of what you see in your population. So you keep pushing that threshold down until you have 20%, or I'm not 20%, sorry, 2%. 2% of your population is being identified as fraud. And then that's where you stop with that threshold. Like, well, I've got my 2%, and those individuals are now what I would identify as fraud. So it's one example, that's binary classification. The other example, I had to remember it, I apologize. The other example was used for claim routing. We wanted to predict the duration of a claim and then bucket it into these different bins, like for it to be managed. And basically, if it was highly likely to return to work within a certain period of time, then it went down one path. And if it was less likely, it went down another path. We wanted to calibrate the model so that the proportion of claims that returned to work in 2 years or less was actually represented by the probability that we're reporting. So if we said 30% of claims returned to work in 2 years or less, we wanted to make sure that in our data set, we're actually predicting 30% of claims as that category to return to work in 2 years or less. Okay, so here is a visual that you can use to tell if your model is calibrated. This is a reliability diagram. And if our model is really well calibrated in this scenario, we're going to see an equal distribution at each threshold. That means 10% of our data is from 0.0 to 0.1. 10% of our predictions are from 0.2 to 0.3. 10% of our predictions are from 0.3 to 0.4. So for each decile, it's usually called deciles, for each tenth of a probability, 0.1, 0.2, 0.3, 10% of our predictions are represented in that decile. You can see what this model actually does is there's very low observed probability, predicted probability is 0.1. I think what this is saying, what it should be saying, if I'm reading it correctly, or what I would expect it to say, I guess, is that there are very few predictions in the 0.0 to 0.2 range from the model. There are very few predictions in the 0.8 to 0.1 range, and then there's a lot of predictions here in the middle. And that's pretty typical, like most of your predictions lie between the 0.4 and the 0.8 range. If that's not what this is saying, I apologize, but that's typically what you'll see, actually. And so we want to push that distribution so there's equal representation across every single threshold. So we're just we're not changing the order is the important thing. If you had a person here and a person here, we're not changing the order. We're just pushing them, we're pushing them apart. So in this distribution, for example, we talked about the uniform distribution. Remember earlier we said, there's this is what in this example we're trying to capture is a uniform distribution where there was an equal probability, an equal count represented in each probability threshold. But you can see this is what our model is actually predicting in reality. So I guess in this example, and I think this is actually what the graph was saying in the other one, it just didn't make sense to me. But in this example, it's saying there's a lot of probabilities between 0.8 and 0.9, not so many here in the middle. This is a count, right? There's 350 predictions of 0.2 and 0.1, and there's no predictions close to 0 and no predictions close to 1. So this is a count of a data set of maybe 1,000 records or so. And this is how the probabilities are distributed across these probability deciles. It's grouping the count by probability. If this was a well-calibrated model, in this situation, it would have a uniform distribution. So we'd cut some of these off and we'd push them this way, and we'd push some of these this way, And we'd basically spread everything out a little bit, push some of these values down in the same order that they exist today, so that it's a uniform distribution. So there's equal representation across every decile. Okay, so model calibration. A model is considered well calibrated if the predicted probabilities are reliable estimates of true probabilities. So in that scenario we said before, in this situation, we're saying that we want a model where a tenth of the time it predicts 0.1, a tenth of the time it predicts 0.2, a tenth of the time it predicts 0.3. Calibration ensures that if the model predicts a 70% chance of an event occurring, the actual occurrence of rate of that event is close to 70%. So it's the whole point of model calibration, is that it's a communication thing, because like I said, the actual order of the probabilities don't matter, and you could just change your threshold and it wouldn't really matter. But when you're communicating to your stakeholders and you're saying that the model had predicted a probability of 0.7, that you would hope that that actually represents a 70% chance of that event occurring. They're going to interpret it that way, so it's best to calibrate the model so that it really is represented that way, and it makes it easier for us to use and make decisions on. So in a perfectly calibrated model, the average predicted probability over all the instances equals the observed frequency of positive outcomes. That's what I was saying about the fraud thing. So our observed frequency of positive fraud outcomes is 2%. In our perfectly calibrated model, the average predicted probability over all instances should equal 2%. There's a lot of different methods. We're not going to dive into the different methods. I think it's enough to introduce the topic for this class. We're really focused on getting deep into the metrics, but I did want to bring up calibration methods as a way of making a really robust model. So I listed a few methods here. Plat scaling, kind of probably the most common method. Oh, I even said that was the most common method. So you can do calibration plots like I had for the other one, and you can put multiple models on there too. And you can say that by nature, one model is better calibrated than another model. For example, here we have log reg and random forest in orange. The log reg by nature is a better calibrated model than random forest. It's a closer fit to that line, though it needs to be spread out a little bit. But you can tell that just the random forest is further away from representing reality from the way that the probabilities are distributed. Now, yeah.
Next question. So if you're looking at that, you're saying, okay, random forest is not the best way to go. Then that allows your team to say, okay, only look at log reg or just regression models moving forward for the specific one.
That's a good question. This calibration is not an assessment of model performance.
Got it.
So calibration does not say how well your model does. Honestly, the log reg in this example could be terrible. It could just have an awful performance. So yeah, no, that's good. But
then I give up.
The way that it represents the probability distributions is much more even than the way that the random forest is representing them, and that could be a data thing. There can be a lot of reasons for that. But if you have two models that are really close to each other, you might look at this and say, well, one of these is going to take some work to calibrate, and we're going to want to make sure we represent those, or it's just kind of like interesting. And that's why I didn't put in any of the homework or exercises, because definitely for this class, much more important to focus on the metrics and the performance. So this isn't a performance metric. It's more of understanding the distributions of your probabilities compared to real world probability distributions. I'm having trouble wording that in a cleaner way. It's more about saying, when I make a prediction that an event is going to occur, when I say, I almost said when I say it rains 3% of the time, but that's actually a terrible example because that's not what, that's not how weather calculates probability. Actually, fun fact, it's a coverage thing. But yeah, you know that.
Yeah.
Okay.
I found that out later in life, but yes.
Yes, so I really try to stay away from using weather for examples. It's actually not what people think it is. Let's see. The fraud one, and then let me see if I can think of a different example. What is the probability that I'm going to start class 8? So I'm going to start class late.
Right.
So you would want, if I told you there was like a 30% probability that I'm going to start class late, probably higher, you would actually want that to represent real world probability. So you would expect that out of every 10 classes you showed up to, that 3 of them I would start late. But then you get halfway through the semester and you're like, well, you showed up late to like 6 classes. That's not 30% probability. I'm like, well, I mean, my probabilities weren't calibrated, so it didn't actually represent the real world occurrence. I mean, it made sense to the model, but their probabilities were squished into this little domain that wasn't spread evenly between 0 and 1. So it's more for us and our own comfort as humans being able to interpret it because we like to compare everything to each other. So it's okay, perfect. Anyways, less important than the other topics, so just touching on it for
For sake.
yes. So model calibration ensures that the predicted probabilities output by the machine learning model are reliable estimates of true probabilities. It's quite honestly for our own human comfort and our assessment of what we might expect an event to occur and comparing it to how many times it actually does occur. It doesn't actually make any quantifiable difference on your model performance. It's just an ordering. I shouldn't say ordering. I'm trying not to use that word because we're not actually changing the order. It's just a scaling or a broadening of the domain of range that these probabilities can be mapped to. Well, I said it can impact the model's performance. That's not particular model's use. It can impact the model's use in practice is what I meant. Okay. That is all I have for today. I'm going to stop the stream, and then, as promised, I'm going to ask you guys if you have any questions after stopping the recording.